Hello dear all, today we are going to talk about introduction to radiation, and then we will talk about the radiation characteristics of black bodies. So when we say BB, it means it is black body. Okay, so first we will start with the EM spectrum of the electromagnetic waves. So we have on one side 10 to the negative 8, so this one is the wavelength in micrometers. Okay, this one is the microns. And on the other side we have 10 to the positive 8, again microns. And we have cosmic rays, the gamma rays, X-rays, okay, ultraviolet. And the ultraviolet means this part is the violet of the visible range, and then to the left is ultraviolet, and then here you have the red, and to the right is infrared, more than red, and then we have the microwaves, and then radio and the TV waves. Okay, so the thermal radiation, so this part where you have 10 to the negative 1 to 10 to the negative 2, this spectrum of the electromagnetic wave is called the thermal radiation. Okay, so and you can notice that some part of the thermal radiation is in visible range, and the visible range of the electromagnetic spectrum starts from 0.38 and ends at 0.76. Okay, so what is thermal radiation? Firstly, what is electromagnetic wave, and then we can talk about the thermal radiation. Electromagnetic wave is when you have the accelerating charge. So when you have accelerating charge, these accelerating charges create EM waves. Okay. And for the thermal radiation, this accelerating charge in thermal radiation, it is due to temperature. Okay, because if you have an object with some temperature greater than 0 Kelvin, it means that the molecules or atoms of the object are accelerating. Atoms, molecules, okay, accelerate due to temperature. This acceleration of atoms or molecules, because they are containing some electrons, so these electrons creates electromagnetic wave, and this electromagnetic wave is spreading in all directions. Okay, you have electromagnetic wave in all directions, and this is called the thermal radiation. Okay, so you have accelerating charge. This accelerating charge in thermal radiation is only due to temperature. Okay, and as you notice, the main part of the thermal radiation falls in the visible range. So what are the examples of the thermal radiation? You have the example as the incandescent light bulb. So this light bulb, it glows, okay, when heated. So if you heat the light bulb material, which is the tungsten, so here we are using the tungsten. If you heat it, after some point it starts to glow, and since it glows, some part of it is in our visible range, and therefore we can see the light. Another part is the hot metal pieces, and when the metal pieces are very hot, for example the oven plate, okay, when it is very hot and you can see the color of it, okay, sometimes it is red and sometimes it is blue, okay, but the one thing you should notice is that the thermal radiation is from 10 to the negative 1 and 10 to the positive 2. It doesn't mean that you will always see the thermal radiation. So if it is in infrared range, we cannot see it, or if it is ultraviolet range, again we cannot see it. And also the concentrating solar power. So this one is the lens here. So if you concentrate the solar power on some point, you will see that there is a burning. Okay, again you can notice the thermal radiation in some focal point of the lens. Or the microwave or oven, so this one is again the thermal radiation. It uses thermal radiation. Say that this is the oven, and here you have some food. Okay, what happens is that you are sending some waves into that food, okay, and these waves are converted into thermal energy or internal energy of the food, and its temperature increases, and then it is cooked or boiled if it is some liquid. And then human body, there is also the thermal radiation from the human body. So if you notice the energy balance of the human body, you can see that some part of the heat transfer from the body is by radiation, which is 40%. Okay, this one is thermal radiation. But the problem is that here we cannot see the thermal radiation because the heat transfer from the human body falls in infrared range of the thermal radiation, which is impossible for eyes to detect it. And then the campfire heat, so this one is again the thermal radiation. Sun heat, this is again the thermal radiation. Why these two are thermal radiation? Okay, one thing we should notice is that if you have the air in heat transfer in between two objects, and if it doesn't move, okay, and then it means that the conduction is much smaller than the radiation. Why? Because the conductivity of air is 0.027. Okay, since the conductivity of air is very small, it means that the heat transfer that happens through the air is mostly radiation. Okay, or this is the window of your house, and the sun heat transfer that comes through the window is again by thermal radiation, because as we have said, the conductivity of air is very small if it doesn't move. If it moves, it is forced convection, and then the radiation effect will be as the same important as the forced convection. But if the air doesn't move, then the conductivity is very small, and then the heat transfer that happens through the air will be radiation. Okay. So another radiation heat transfer can be a very simple experiment that you can do by yourself. If you put your hand very close to your face, so this is your hand and the palm of your hand, very close to your face, you can feel the thermal radiation from your hand to your face. Okay. And these are the experiments or the examples of the thermal radiation. There are a lot more than these experiments, but these are giving intuition about the thermal radiation. So if you go back to the X-ray, and okay, another important thing about the thermal radiation is that, very similar to X-ray picture of our hands, we can take the thermal image of an object, because if you have a temperature that is greater than 0 Kelvin, then it means that there is always thermal radiation. Okay, for the thermal radiation, the temperature of greater than 0 Kelvin is enough. So here we have the temperature of around, say, 100 degrees Celsius, but since this temperature, thermal radiation from the body, since the thermal radiation from the body is not in the visible range, in this range, we cannot see it. Okay, so since we cannot see it, it is in infrared range. We will see in the next slides why it is in infrared range. So these electromagnetic waves from the body is in infrared. So if you have some detector that is sensitive to infrared range, we can see the picture of the kettle. So some animals, for example snakes, okay, they can detect the infrared rays. Okay, but this one is done by thermal imaging. Okay. And they have the sensors that is very sensitive to the infrared range, and then you can take the picture. And where you have the sharp sides, it means that it is very hot, and when you have the dull sides, it means that it is cold, or this part is cold. Okay, so now comes the important part of the thermal radiation. Thermal radiation is very complex. Okay, the complexity of the thermal radiation we can understand from this example. Say that we have one body at T1 and another body at T2, and we are trying to understand what is the heat transfer from 1 to 2, net heat transfer, okay, from 1 to 2, and this net heat transfer is the difference between from heat transfer from 1 to 2 and from 2 to 1, because as we have said in our previous slide, for the heat transfer in thermal radiation, temperature greater than 0 Kelvin is enough. It means that even if T1 is greater than T2, T2 will also transfer heat from the T1. Okay, and at the same time, T1 will transfer heat to T2. Okay, for thermal radiation, the amount of heat temperature is not important, but the value. If it is greater than 0 Kelvin, then you have the thermal radiation. Of course, body 1 will give off more heat transfer to body 2 due to its temperature, but body 2 at the same time will transmit heat from itself. So the net heat transfer depends on the temperatures of the surfaces. It is very clear. High temperature means higher heat transfer, Areas of surfaces, again, higher area means that larger area means larger heat transfer. And the shape and the orientation of the surfaces, it is also important. For example, if you have the different orientation, so we'll talk about this one in our next slides, but for the simple example, say that I have a surface like this one, I have another surface like this one. Okay, so this surface transmits radiation in that direction, say it's in that direction. This surface has very low possibility that it will see this surface. Okay, surface 1, and this one is surface 2. Surface 2 transmits in that direction, and the surface 1 transmits in that direction. So it means that net heat exchange between these two bodies is 0, because it is very low possibility that you have you have the radiation that goes in that direction. Okay? It is very low possibility. Therefore, the orientation of the surface is very important, and the shape also is very important, because if you have a body something like this one, then the heat transfer from the body will hit itself, okay, and then again back to hit itself. Therefore, some part of the radiation will be lost at the body itself instead of traveling to another body. Okay, and now comes the next part, spacing between the bodies. It is also important. So the distance, let's say I have a distance d here, it is very important. And the radiative properties of the surfaces, how it absorbs, this one is absorb, and how it transmits, second one is transmit, and the last one is the reflect. Okay, that the values of these are important. So if the body reflects the radiation, it means that its internal energy will not increase too much. And additional surfaces, so if you have, for example, air, you will have different heat transfer. If you have the vacuum, you will have different heat transfer. If you have the, let's say, that water vapor, you will have different heat transfer. Okay, because the medium that is participating in between the bodies will affect the thermal radiation. And the last one is this one is the last one, medium. And we have one more thing that I have forgotten, additional surfaces that may reflect the radiation. So this one is, say that I have a surface here, okay, and the radiation from this body leaves in that direction, and the next one leaves in that direction, the next one leaves in that direction. Okay, say that I have a surface something like this one. This is this additional surface. This additional surface will reflect the radiation back. Okay. If I have another surface and it goes back to T1, now you can notice that it is very similar to tennis ball. Okay. It bounces off from one surface and it goes in another surface and it goes to T1 again. It is also possible that the radiation that travels from T2 to T1 is absorbed here. So say that I have another surface here. The radiation that leaves from that surface, and it doesn't reflect off from the surface again, and it becomes its internal energy. Okay, and it doesn't mean that it will always reflect it, or it can also emit it. Okay? It can emit this one. And emission and the reflection are different things that we talk about in our next slides. Now comes the main important topic of our lecture, which is the black bodies. And firstly, what is black body? The black body is it is an ideal body. Okay. What it means is that black body, so it absorbs all radiation. Okay, this is the first thing, and the second thing is that it emits all radiation. Okay. It emits all radiation. This is the two important things about the black body, or you can see here that independent of direction or wavelength, it is independent of the incident radiation. If you have some incident radiation to the body, independent of direction and the wavelength, it absorbs all of it. Okay, and it neither transmits and nor reflects. Say that I have a body and I have thermal radiation on it, and thermal radiation on it, thermal radiation. Independent of the direction, all of these radiations are absorbed by the body. Okay, it becomes the internal energy of the body. Okay, and neither transmits that it doesn't pass through the body, and it is not reflected. It means that it is not. It always becomes the internal energy of the system. And it is diffuse emitter. Diffuse emitter means that after it has become the internal energy of the system, now it starts to emit it. Okay. and emits in all directions at the same amount. Say that if it is direction 1, it is 5, direction 2 it is 5. If I go in another direction, it is 5 again. So it means that if I put my hands here, I will feel the same heat, or if I put my hands here, I will feel the same heat. So independent of the directions, it emits at the same amount. And it is the maximum emitter. So here one thing I should say that, I will talk about this one also. So emission versus reflection. Okay. So emission and the reflection are happening at the same manner. So if you have a body, it emits, and if you have a body, it reflects. Okay. The main difference between emission and the reflection is that reflection is not part of internal energy, but emission is part of internal energy. So it means that if body emits, its temperature drops. Okay. But if body reflects, its temperature doesn't change. This is the very important thing. For example, snow. Okay. Snow reflects in visible range. Okay, it is very important. In visible range, it reflects. Therefore, its temperature doesn't change in visible range. But if it emits, and then its temperature will drop. So emission is part of internal energy. Therefore, if body emits, its temperature drops. But reflection is not become part of internal energy, and rays come and bounce off. And what are the examples of the black body? So black body examples can be black paint, water, vegetation, human skin, soil, there is a comma here, soil, red brick, etc. These can be approximated as black body at 300 Kelvin. If you are 300 Kelvin we are 27 degrees most of the time. Therefore, these bodies can be approximated as black body because they have very good emission. Okay. And one more thing here we should notice is that the black body doesn't mean that the color is black. For example, I have given some example here for snow. Okay, snow is white in visible range because when we see the snow, it is white, it is very clear. But when it is infrared range, it is black. Or you can say that, as we have said, snakes can see the infrared range. So snakes see the snow as black, but our eyes see the snow as the white. That is the very important thing about the black body. So the black body means that black body is not about the color, but it is about the property of the material. So there is a theoretical example of the black body. So say that I have a surface or material, something like this one, and there is a small hole here. Okay, and there is a thermal radiation into that body from some other surface or the environment. What happens is that thermal radiation, so this one is not possible to travel into the body. Say that there is thermal radiation, something like this one. Okay. This thermal radiation is transmitted into the inner surface of the body and comes, and it can be reflected here. It is possible. It goes another surface, reflected. It's another surface, reflected. It's another surface, reflected. So you can see that it is reflected a lot, and after reflection of multiple times, it becomes internal energy of the system. Okay. And so this means that whatever ray that is incident on the body, it absorbs all. It absorbs all incident radiation, thermal radiation. Okay. So therefore, first property of the black body is valid here. So it means that independent of direction or wavelength, it absorbs all of it, and it doesn't transmit. This body does not transmit, because this is opaque body. It doesn't reflect. Reflection here in this case is very different. Reflection means that it reflects and leaves the body, but in this case it doesn't reflect because multiple reflections happen inside the body, and that reflections becomes internal energy of the system. Therefore, first property is valid, and now comes the second property, which is the diffused emitter. Let's see the second property. Now, but what happens is that this body emits this body emits thermal radiation. If it emits thermal radiation, it leaves from that surface, part of the surface, to here, and then to that one, and then to this one, and leaves. Okay, this is the one direction. And say that I have another emission here in this direction. It comes here, it goes there, it comes here, and leaves in that direction. Again, if you do this multiple of times, you will have the emission of the thermal radiation in all directions at the same amount. Okay, same amount in all directions. And therefore this one is the diffuse emitter. And independent of this, we have the first property, second property, and the maximum emitter, because here emits all of the radiation, and we have small hole, one small hole. There is a possibility that all of the emission will happen from this hole at the same amount with the maximum amount too. Okay. So another property of the thermal radiation is that it depends on the spectrum. The spectrum means that lambda. Okay, you can see that the radiative property can change in any manner with respect to lambda. So it means that it is function of the lambda. Okay, and it is also possible that it is constant with any lambda. So if you have whatever value you change with the lambda, the property doesn't change. And another thing about the thermal radiation is that it depends on the angle. So you can see here, in this case, the thermal radiation is same in all directions. It is hemisphere. But in this case, this one is called the diffuse emitter. In this case, it is not the same in all directions. In one direction it is more, in other direction it is less, and in some directions you don't have any thermal radiation. Okay? This one is most of the case for real surfaces. And this is the second property of the thermal radiation. And the last one is that it is function as a function of the temperature. So that if you increase the temperature, you will have to change something like this one, or you can have to change something like this. Therefore, these three things makes thermal radiation very difficult and complex. And now we have come to the last most important part of the thermal radiation, which is the emissive power, or E lambda. So E lambda, this one is the emissive power. So if you look at the unit of it, you can understand what is emissive power. It is watt per meter square and multiplied with micrometer. So what it means is that it is the emitted power from the body. So power emitted, it is emitted power from the body per unit area, for one area and one wavelength. Okay, so we are looking for the emitted power per wavelength and per area. Okay. So we have the different temperatures. We are changing the temperature, and also we are changing the lambda, and we are trying to understand what is the emitted power from the body. So if you look at the 25 degrees Celsius, what is the emitted power from the black body? This is true for black body. What is the emitted power from the black body at 25 degrees Celsius? You can notice is that we have at 100 lambda, and we have started from the 100 lambda, and it comes to some point around here. So you will have a change of emitted power, something like this one. You have some point, the maximum, and then it drops, and it drops on the other side too. So as you can notice here is that this part is the visible range, and for 25 degrees Celsius emitted power is not in visible range. It means that for any body, any object around us, we cannot see its color, because the power emitted from that body is not in visible range. If you go to 250 degrees Celsius, again you can notice that there is no any visible range for that temperature. But for 500 degrees Celsius, and some part of it falls in the visible range. It means that if you have an object at 500 degrees Celsius, you can see the color of that object, and you can see the change for 1500 degrees Celsius. You have more visible range, and 25 and 55. This temperature is the surface temperature of the sun. This is the surface temperature of the sun, and you can notice that most of the peak wavelength of the sun comes in the visible range, where our eyes are very sensitive. We will talk about this one as an example. And if you connect the maximum emissive power of the black body at different temperatures, and you can notice that this one is the linear. Okay, and this linear range gives you the maximum emissive power of the black body, and the relationship is this one, lambda max, the maximum lambda into the temperature is equal to constant, and this is called the Wien's displacement law. Okay. And then the last thing is that for the emissive power, the relationship is this one, C1 lambda to the power of 5 exponential C2 by lambda t negative 1. This one is constant, this one is constant, and this relationship is called the Planck's law. Okay, and the graph plotted here is the graph of this function. This function plotted here as a graph. Okay. And if we analyze the simple example of the sun energy that reaches on Earth, you can see the values that are given. 6% is reflected by atmosphere, so it means that the sun energy that comes on Earth, and the 6% is reflected here, atmosphere, and 20% is reflected by the clouds. We have the clouds here, 20% it is reflected, it doesn't reach the Earth, and the 4% is reflected from the Earth, again 4% it is not reaching the Earth, and you have 6 plus 2 plus 20, and it makes 30% doesn't reach the Earth. Okay, it is reflected. And then, so reflected means not part of internal energy of the Earth. And the 51% is absorbed, so it becomes the internal energy of the system. And the 16% is absorbed by the atmosphere. So here you have the 16%, and the 3% absorbed by the clouds. Okay. And as you see from here that the heating of the ground, okay, heating of, let's say that the Earth atmosphere okay. Now if you see the opposite case, the energy leaving the Earth, and you can see that 15% the energy that is leaving the Earth is emitted by as radiation the clouds and the space. So because 51% is absorbed, and now the absorbed energy will be emitted, and this energy will be emitted 15% to clouds. You have 15%, maybe another color here, 15% to clouds, again 15% to clouds, it is emitted. So if you see emission, it means that it is part of internal energy, so the temperature may drop, but since it is in thermal equilibrium, the temperature doesn't drop. 7% as the conduction, and 29% as water vapor and the clouds. And one more important thing here is that the ultraviolet rays of the sun energy is stopped here at ozone layer. Okay, ozone layer is not transmitting the ultraviolet energy from the sun, and since it is very dangerous, it is very dangerous for us, and ozone layer prevents that ultraviolet range from the sun. Okay, now the one thing about the thermal radiation is the fraction. This one is the F fraction. Okay, what is this F? Okay, if you go back to here, I have the function emissive power as the lambda, and the temperature it is given as this one. So first thing is that if I integrate this lambda with respect to lambda from 0 to infinity for all of the wavelengths and for all of the lambdas, if I integrate it, I will get sigma T to the power of 4, which is the black body emission. Okay, the famous thing that we know. So this one can also be integrated with some arbitrary lambda, lambda 1, E, lambda T, D, lambda, and if I divide it by sigma T to the power of 4, I will get some fraction at lambda 1. So it means that the black body emissive power between 0 to lambda 1 to total emissive power gives me the fraction of it that falls in this range. Okay. As a simple example here, so it says that find the radiation of the sun that is in visible range. So before using the table, let's write the equation for this one. The visible range is from 0.38 and lambda 2 is 0.76, or I can write this one as lambda 2 and lambda 1. And it says that find the fraction of the sun energy that falls in this range. What is the fraction, or what is the percentage? Okay. What I will do is that I will integrate from lambda 1 to lambda 2 E lambda temperature D lambda that is given here, this equation, divided by sigma T to the power of 4. Or this is the first thing that I can do by analytical methods, or I can write this one as from 0 to lambda 2 E lambda minus 0 to lambda 1. This is the same equation. I'm using the property of the integrals, d lambda, and I can divide these total quantities by sigma to the power of t to the power of 4. These 0 to lambda 2 or 0 to any lambda, integral of lambda t d lambda divided by sigma t to the power of 4 is tabulated. Okay, it is given in tables. This ratio is given as in tables, but it is given with respect to lambda into t. Okay, but here you should start from 0. Because from 0 to lambda, and you divide with sigma to the power t to the power of 4. And if I do this example, firstly I will first find the lambda into temperature. So lambda 1 is 0.38, and the temperature of the sun is 5500 plus, it should be in Kelvin scale. This one will be lambda 1 T, and this quantity, if I find this quantity, and if I will see the fraction here. So if it is 0.1, it means that 10% of the black body emissive power is between this range, is between from 0 to 0.38. And if I find, for example, 40, it means that the black body emissive power, 40% of the black body emissive power is in this range from 0 to lambda 1. Okay. And now let's find it. First, lambda 1 into temperature, it will be 0.38 multiplied with 5773, and the lambda 2 T, it will be 0.76, again the same quantity. And from here I will find the fraction from the table, and I will find fraction from the table. Let's calculate it. So if I calculate the first one, it will be 0.38 into 5773. It is 22 hundredths. The first one is, if I go back to here, for 22 hundredths, F is 0.1. Or it means that the 10% of the sun energy is from 0 to lambda 1. Okay. And now comes the second part, lambda 2 into temperature. Let's find it. Makes 44 hundredths. I'm using the approximate values. 44 hundredths, and it is 0.55. So what it means is that if I go back to the chart here again, it means that the sun energy, this part is 0.38 and this part is 0.76, and for the sun chart is this one. Till that part is 10%, okay, until this part is 55%. Okay. What I'm doing is that I'm integrating these quantities. So let me write it. I'm finding the area below it. So I'm trying to find what is the area here. Okay. For the first lambda one, it makes area but divided by the total sigma t to the power of 4. And the area of this one divided by the sigma t to the power of 4 makes 10%. It means that the total area here underneath this line, you have the total area. The 10% of the total area is here, and comes the second lambda. For the second lambda, it means that the 55% of this total area, the total area is here, 55% of the total area falls in that range. Okay. If I subtract it, so 0.55 minus 0.1, it makes 0.45 or 45%. It means that 45% of the area falls in this range, which is the visible range. Or in other words, the sun energy that reaches the earth, and it's 45% is visible, and which is important for our eyes that can see in this range. And now we have talked about, till this part we have talked about only for one black body, and now let's see if we have two black bodies, what will happen. For two or more black bodies, we will talk about the V factor. Okay. What is V factor? V factor is shown as the F. So if it says, say that surface 1 and this one is the surface 2, if it says from 1 to 2, it means that the V factor from 1 to 2. Or if it is F to 1, it means that V factor from 2 to 1. So what is the definition of the V factor? It says that radiation leaving surface I, let's say 1, that goes directly to surface 2. Okay. Radiation leaves the surface 1 and leaves the surface 1. It can be reflected or it can be emitted, okay, and reach surface 2 directly. Okay, it's very important, directly, because if I have a surface here, it goes back to here and then here, it is not counted. Okay, and the total radiation leaving surface R, and this is called the V factor. In other words, in simple terms, you can say that half surface I sees surface J. Okay. Half surface I sees surface J, and this is called the V factor. And this F12 shows the fraction of radiation that reaches from surface I directly to surface J. And to find this fraction F12, we have the equation here, the integral. Okay, and the theta I is that this one is the normal to surface. Theta I is the difference between the angle difference between the normal to surface and this vector that connects these two surfaces. Okay. But the theta j is also the angle between this distance. Okay, you can also say that the distance between those two surfaces. And to integrate this quantity is very difficult. So what we are doing is that we are using the charts, tables that are giving the V factor. So if I go back to the radiation part here, and we have tables that shows us the radiation V factor between any surface. This one is surface I, this one is surface J. You can have the surface something like this one, you can have the surface something like this one. For different surfaces, we have the tables or the charts. Okay, you can have the chart for the two surfaces. How do you find its V factor? Now we'll talk about the V factor relations. Okay, the first relation for the V factor is that the summation rule. Okay. So for the summation rule, I can talk about this simple example here. I have the surface 1, I have the surface 2, and I have surface 3. Okay, the radiation, the fraction of radiation that leaves surface 1 to surface 2, that leaves surface 1 to surface 3 and the surface 1 to surface 1 itself. In this case, it is not possible that the radiation leaves surface 1 will heat itself, but in some cases it is possible. For example, for this one it is possible. But for the general rule, the fraction of the radiation that leaves surface 1 to itself, the second surface and the third surface, it will be 1. Or you can write as a general rule I to j, I is from 1 to n is equal to 1. So j is from 1 to n if I to j is 1. This is the first rule of the V factor. And if there is no surface, say that I have two surfaces here, I can add the third surface here, which is imaginary surface. Okay, I can add imaginary surface here and write the same relation here. Okay, the next rule is the reciprocity rule. Okay, what is the reciprocity rule? Reciprocity rule is that area 1, F1 to, you can write the general, but I'm writing the simple terms, area 2, F2, 1. So this one is the surface 1, the area of the surface 1, the fraction of the radiation that leaves from 1 to 2 is equal to the area 2, fraction of the radiation that leaves from the surface 2 into area 1. Okay, this is the reciprocity rule, and these are the two important rules that we are using for the thermal radiation. And here there is a simple example. I have a surface 1, and these are the radiation that leaves the surface 1, and the sum of it reaches surface 2. I can write that if these two are black bodies, okay, we are always talking about the black bodies. The thermal radiation that leaves surface 1 is sigma T to the power of 4. This one is surface 1 and this one is surface 2. And the sum of it reaches surface 2. So this one is F1, 2 that reaches surface 2 into sigma T to the power of 4. Okay, and I should write also the area here, area 1, AS1 and also the AS1. Okay. This is the radiation that leaves surface 1 and reaches surface 2. Similarly, the same thing happens for the surface 2. Some radiation leaves surface 2 and reaches surface 1. So this one is Q dot 1 to 2. They can write the same stuff as Q dot from 2 to 1. It will be the view factor from 2 to 1 into the same temperature. So say that this one's temperature 1, this one's temperature 2, and AS2. These are the net heat exchange between 1 and the 2. And the net heat exchange between 1 and the 2, it will be the difference of this one, F1 to 2, and the sigma T1 to the power of 4 AS1 minus F2 1 sigma T2 4 AS2. Okay, and if T1 is same as T2 or the thermal equilibrium, then Q dot 1 to 2 net. Q dot 1 to 2 net will be equal to 0. There will be no net heat transfer. There will be heat transfer from 1 to 2, 2 to 1, but net heat transfer will be 0, and the T1 and T2 will be equal, and F1 2 into A1 will be exactly same as F2 1 into area 2. You can see the same relation that we have said in reciprocity rule. Okay. In this case, we have approximated that the temperatures are equal, but the result is independent of the temperature. So this one is independent of temperature. And since the net result is only dependent on the geometry, it means that it is true for any case, whether there is thermal equilibrium or not, because the final result is independent of the temperature.